Picking up where we left off, we're going to do types of matrices. Now we have a lot of types of matrices we have to deal with. The first type is a column matrix, and the column matrix has one column only. Example A, B, and C, they all have one column only. Remember, columns run vertically. A row matrix is analogous to a column matrix where it has only one row. X, Y, C has one row only. As you can see, a matrix with one entry in it can be considered both a column and a row matrix, because at the same time it has one column, it has one row. Number 3, the null or the zero matrix. It's just a matrix that has a whole bunch of zeros in them. Regardless the size, every single entry is a zero. Number 4, the singular matrix. A singular matrix has a determinant of 0, and we will speak about the determinant probably in this video or in the next video. The identity matrix, very important. The identity matrix, we only need to know it for 2 by 2 matrices, is 1, 0, 0, 1, and it's symbolized by a capital I. Now, what is the identity matrix? Just like in numbers, we have the identity for numbers. Think of matrices as a different branch of numbers. The identity for numbers is such that if I have a number multiplied by the identity, I get back the number. So for example, 2 multiplied by something will give me back 2. And what is that something? That something is 1. So my identity for our regular number system is 1. Similarly, the identity for matrices will be 1, 0, 0, 1. That follows the same properties. If I have a matrix multiplied by the identity, I get back the matrix. Just like I have a number multiplied by the identity, I get back the number. So the identity for matrices works in such a way that any matrix A, any 2 by 2 matrix A multiplied by the identity will give me back A. It works the other way around as well. The identity multiplied by a matrix, remember both of them needs to be 2 by 2, the identity by a matrix will give me back the identity. Okay? Lastly, the inverse matrix is such that A by its inverse will give me the identity, or the inverse multiplied by A will give me the identity. And again, this will be similar to that of the number system. If I have the number system where I have again the number 2, 2 has an inverse of 1/2. Now, some students might think the inverse is just -2. No, the inverse is when we flip it. As it stands, this number 2, it's over 1. When I flip it, it becomes a half. And if we perform this operation for our regular number system, a number multiplied by its inverse will give me the identity for that branch of numbers. The similar thing happens for matrices, where a matrix multiplied by its inverse, it will give me back the identity for matrices. So let's go on to talk about 4, 5, and 6. So number 4, singular matrix. A singular matrix has a determinant of 0. So we end up with determinant. So let's see what the determinant is. The determinant of a 2 by 2 matrix is calculated as follows. Now it's just a number. So if I have a 2 by 2 matrix A, B, C, D, my leading diagonal will always start from the first entry and end at the last entry. So this is called my leading diagonal. Right, it's just a terminology we use. BC, that diagonal, we refer to that as the other diagonal. So let's give this matrix a name A. The determinant, and we abbreviate determinant with DET of A, or the determinant of A, where A is between 2 straight lines, that's another symbol for the determinant of A, is equal to the leading diagonal, which is AD, take away the other diagonal, which is BC. For example, if I have A being the matrix 1, 2, 3, 4, then the determinant of A, or the determinant of A is equal to the leading diagonal 1 by 4, take away the other diagonal 2 by 3. 1 by 4 is 4, 2 by 3 is 6, we get negative 2. And this applies for all 2 by 2 matrices. Now we have the case where number 4 was a singular matrix. Now what happens with the singular matrix? For A, we can conclude that this matrix is not singular because it has a determinant of negative 2. Now how questions will come for singular matrices will be like this. If A is singular, where A, let's say it's 2, 0, 1, x. No, I'll put 1. Calculate the value of x. So the first thing we'll take out of this is that a singular matrix has a determinant of 0. So the determinant of A will be equal to 0 because A is singular. Well, let's calculate the determinant of A. It's the leading diagonal 2 by x. Take away the other diagonal 1 by 1. 2x take away 1, and remember we let in the determinant of A be equal to 0 because the determinant of a singular matrix is equal to 0. So 2x minus 1 is equal to 0, 2x is equal to 1, and x is equal to 1/2. So when x is 1/2, this is the value that makes A a singular matrix. All questions for singular matrices will come the exact same way. Alright, so I'm skipping the identity for now and I'm going straight into the inverse. Now, if you realize we did not do any division of matrices, right? So instead, we'll do an operation called the inverse. So how do we calculate the inverse of a matrix? Calculating the inverse of a matrix. 1. The inverse of a matrix is symbolized as A inverse if the matrix is A. If the matrix is B, it could be B inverse. If it's C, it will be C inverse, and so on. There's a formula. A inverse is equal to 1 over the determinant of A multiplied by the rearranged A. Oh yeah, got to ask yourself, what is the rearranged A? So we'll go into rearranging a matrix here. Rearranging a matrix. If A is the matrix A, B, C, D, to rearrange A, I must flip the leading diagonal, meaning I must interchange the numbers on the leading diagonal. So A becomes D and D becomes A. And I change the signs in front of the numbers on the other diagonal. So this is B, it will be negative B. This is C, it will be negative C. Let's put some numbers straight and see what's going on. For example, if A is 1, 2, 3, and 4, the rearranged A, I must flip the leading diagonal. So the 4 comes where the 1 is, and the 1 goes where the 4 is, and I change the sign on the other two. Minus 2, minus 3. That's it. Do another one. If B is minus 2, 6, minus 4, minus 1, again, the rearranged B is equal to, I must flip the leading diagonal, minus 1 and minus 2, change the signs on the other diagonal. This was positive 6, it becomes negative 6, negative 4, it becomes positive 4. And that's it. We already know how to calculate the determinant of a matrix. We already know how to rearrange a matrix. So we know how to calculate the inverse of a matrix. So let me see what we have. So I'm going to calculate the inverse of 1, 2, 3, 4. So calculate the inverse of A, which is equal to 1, 2, 3, and 4. And we learn a new property in the calculations here. Well, we know that our A inverse is 1 over the determinant of A multiplied by the rearranged A. We already have the determinant of A. The determinant of A from above is given as minus 2. 1, 2, 3, 4, the determinant of A, we calculated it before, it's minus 2. So this becomes 1 over minus 2 multiplied by the rearranged A, which is 4 minus 2 minus 3 and 1. This brings us to an operation called scalar multiplication. Now we'll go to the side. Scalar multiplication is very easy. If I have a scalar, some number k, multiplied by a matrix A, B, C, D, it doesn't matter the size of the matrix, I must multiply that number by each of the entries inside. So this becomes Ka, Kb, Kc, and Kd. For example, if I have 2 multiplied by 1, 2, 3, 4, I must multiply 2 by each of the entries inside. So I get 2, I get 4, 6, and 8. The same thing applies to if I am factoring out a number from a matrix, I must factor that number out of each of the entries. So if I work backwards, I'm factoring out 2 from this matrix, 2, 4, 6, 8. I pull out the 2 and I divide each of the entries by 2 to get my matrix. So let's deal with the scalar multiplication in this case here. I have negative a half multiplied by each entry inside. My suggestion, leave it as a fraction, but without simplifying. The only time you should simplify is if you get a whole number. So for example, negative a half multiplied by 4, and I'll write it out. This is minus a half multiplied by 4. This is minus a half multiplied by minus 2, minus a half multiplied by minus 3, and minus a half multiplied by 1. Minus a half by 4 is negative 2. Minus a half by negative 3 is positive 3 over 2. This is what I mean when I say leave it as a fraction. Minus a half by minus 2 is positive 1. Minus a half by 1 is minus a half. So this is A inverse. Very, very simple. Very, very easy. Now the law above for identity and inverse states if I have the matrix multiplied by its inverse, I should get the identity. So let's try it out and see here. So at the same time, we are going to have a little practice in multiplication of matrices again. So A multiplied by A inverse. This will be 1, 2, 3, 4 multiplied by minus 2, 1, 3 over 2, and minus a half. First things first, check the sizes, 2 by 2, 2 by 2. They can be multiplied. And pause the video, take a couple seconds, and try and determine the size of the matrix. The size of the matrix will be a 2 by 2 matrix. So we write out 2 rows and 2 columns. First, second row, first column, second row, second column. So let's go to calculator. E11. First row, 1, 2. First column, minus 2, 3 over 2. First by first, second by second, 1 by minus 2, plus second by second, 2 by 3 over 2. 1 by minus 2 is minus 2, plus the 2's cancel, we get 3, we get 1. I've seen some kind of progress. E12. First row again, second column, 1 minus a half. This is equal to first by first plus second by second. 1 by 1 is 1, minus 2 multiplied by negative a half is negative 1. 1 plus negative 1 is 1 minus 1, which is 0. Again, I'm seeing things happening. E2, 1, second row, first column, first by first plus second by second, that is minus 6 plus 2 into 4 is 2. 3 2s are 6. Minus 6 plus 6 is 0. And lastly, E22, second row, 3 4, second column, 1 minus a half. First by first plus second by second, 3 plus 4 by negative a half is minus 2. That's 3 minus 2, which is 1. So my solution, A inverse, is equal to E11, E12, E21, E22, which is equal to the identity matrix. So take the exercise where you all will prove that A inverse multiplied by A will give me the identity matrix. So A inverse by A is equal to the identity. Prove this. Right? Take your time and do your questions. Now, I am seeing something happening here for matrices. If you notice, number 6, the inverse of a matrix A inverse multiplied by A inverse is equal to the identity, which is also the same as A inverse multiplied by A, which kind of making sense to us because multiplication is supposed to be commutative. But remember, matrix multiplication, it's a little different from our regular multiplication of numbers. So let's do an exercise. Is matrix multiplication commutative? Let's check and see. Is matrix multiplication commutative? So if I take any two matrices, let A be the matrix, and I'm going to use symbols A, B, C, and D, where A, B, C, and D are any number, and B is the matrix W, X, Y, and Z, again catering for any numbers. I'm going to check if A multiplied by B is equal to B multiplied by A. Is AB equal to BA? Now to do this, I just need to prove one of the entry. So I'm going to show E11 in both cases, and I'll check them out and see. AB is A, B, C, D multiplied by W, X, Y, Z. 2 by 2, it's a 2 by 2. They can be multiplied, and the answer will give me a 2 by 2. E11, first row, second column, second row, first column, second row, second column. I'm going to just calculate E11. E11 is the first row, which is AB, multiplied by the first column, WY. First by first, A by W, plus second by second, B by Y. This is AW plus BY. This will give me some number for numbers of A, B, W, and Y. Now I'm going to check BA. BA will be the matrix B, W, X, Y, Z, multiplied by A, which is A, B, C, D. Again, this is a 2 by 2, this is a 2 by 2. They can be multiplied, and I will again get a 2 by 2 matrix. Again, I'm just going to calculate E11. This will be first row by first column. First by first, which will be W by A plus second by second, which will be x by c. This is WA plus XC. E11 from AB, so E11 from the matrix multiplication AB, it's not equal to E11 from the matrix multiplication BA, which means that these two matrices, they are not equal to each other. And you can take the exercise, plug in numbers for A, B, C, D, W, X, Y, Z, and calculate the entries. So this is a law, and the law says that matrix multiplication is not commutative. With the exception of the identity matrix, of course.